Okay. Okay, it's now being recorded. Hello, everybody. We're trying to start a lost discussion, which is to go over old material as a review, as well as go through new material more slowly. And we're going to be posting a poll about scheduling when that is going to be held. And you should definitely come and check it out, especially if you're feeling more behind. It should be a good discussion. But yeah, so keep an eye out. Thanks.
Right, very good. So yeah, so right, so last time that we talked was before the midterm. Then we had the midterm, and we skipped a lecture due to the elections. So probably like a big gap between the last lecture and this lecture. And actually, we'll start today a new topic, sort of towards talking about this P versus NP question, talking about NP complete problems. Why we consider them as hard problems, and how can we cope with them eventually. So this is going to be like the next topic that we'll cover in the next 4 lectures, roughly. But before we start going, talking about these P, NP, I want to talk about the reduction. And this is, we will start with an example. And then we will abstract away what happened in this example. And actually, as you will see, you are using reductions without even knowing that throughout this course, and maybe even before this course. Reductions is a very common tool in building algorithms. And we will also show how reduction play a role in proving that problems are hard. Okay, so without much ado, let's talk about the first problem for today, which is bipartite matching problem, or BM. So what do we get? We get as input a graph, which is bipartite, meaning that there are 2 kinds of vertices on the left and vertices on the right. So here you can see that there are like 3 vertices on L on the left and 4 vertices on the right. And all the edges go between the left-hand side and the right-hand side. So there's no, like, this edge is not allowed, okay? So this is just the input. And what are we looking for? We're looking for a matching in this graph. What is a matching? It's a set of edges, okay, which we denote by M, subset of all the edges in this graph, such that, there's no 2 pairs that collide. So no 2 pairs touch the same vertex. Okay, so for example, this thing is not a matching because we have here 2 edges that touch the same vertex, but this thing is a matching, right? Because every vertex touches at most, sorry, this is not a matching. Okay, so this thing is a matching, right? Because every vertex touches at most 1 edge, okay? And the goal is to find the matching that has maximum number of edges. Okay, so we want to maximize the size of the matching, the number of edges, and we want to satisfy the property that this is a matching, meaning that every vertex touches at most 1 edge. Okay, so it could be that some of them would touch 0 edges, but it cannot be the case that one vertex touches more than 1 edge in the matching. Okay, so you can think about some motivations for this problem. You can think of like trying to allocate resources to tasks. For example, when hospitals try to hire doctors, there's usually some kind of matching problems going on in the background, where you can think of like doctors as the left-hand side, maybe hospitals as the right-hand side, and maybe an edge saying, if this doctor, can work in this hospital, and whether this hospital wants to hire this doctor. And let's say that every doctor can work in at most 1 hospital, and every hospital can hire at most 1 doctor. So then it's natural to say that this is a matching, and it's very natural that we want to maximize the number of assignments, right? We want the number of hires there's always like a very trivial matching that doesn't match up anything, but that's not that interesting. So we want to maximize as much doctors to hospitals as possible. So, okay. You can also think of motivations coming from matchmaking. So this is like maybe the more traditional story. Okay, so we will show today how to solve the bipartite matching problem by the algorithms that we already saw for max flow. So this would be kind of, intriguing, right? So max flow talks about networks with capacities. We have a source and a sink. And using this algorithm for max flow, we will be able to solve the problem of bipartite matching. And how are we going to do that? We're going to do a reduction. We're going to take an input that is sort of a natural input for the bipartite matching problem. And we're going to construct from it another input, which will be a natural input for the max flow. And then we'll show that a solution for the max flow problem translates back to a solution for the bipartite matching problem. Okay, so let's first see this, how we're going to solve this thing, and then we're going to abstract away what is a reduction. Okay. So maybe let me copy this graph. Okay, so I'm copying this graph. And let's see, how would we convert this graph into a network with capacities? So recall that, in the max flow problem, first, all the edges were directed. And here, we have no direction so far. We just have left and right. And also there's like a source and a sink. So the way that we're going to convert this instance into an instance for max flow is that we're going to introduce like some kind of artificial source S and some artificial sink T or target T. We're going to connect all the, the source to all the vertices in L. We're going to connect all the vertices in R to T. And we also need to orient the edges between L and R. So we're just going to make them move from left to right. Okay, so now we have a directed graph with a source S and a sink T. We also need to say what are the capacities. So we have all the capacities equal 1. And now we're going to run the algorithm for max flow. It will give us some maximal flow. And we want to take what the algorithm is giving to us, the solutions that the algorithm is giving to us, and sort of get from it, extract from it a matching on the original problem. Okay. So one thing that we need to, to worry about a little bit is, when we talk about max flow, what do we require? We require that, the flow coming into a vertex equal to the flow coming out of a vertex, right? But it could be that, let's say that this, like if we're thinking of like what's the max flow here, it could have been that the max flow is like, has some, flow of 1 here, but then this flow of 1 is maybe split into two edges, like maybe half and half. So this will be a problematic thing for us because we would like to think of, the flow as like either 0 or 1, 0 meaning that we are not picking this edge to the matching, and 1 meaning that we are picking this edge to the matching. So this solution is kind of problematic for us. So the way that we're going to handle that, okay, so the question is, what if a flow gets split? So the way to handle this is to notice something about the algorithm or the solution that we had for max flow. And we have the following fact, which I will not prove, but it sort of follows by inspection. If you look at the algorithm, the Ford-Fulkerson algorithm, it says that if all capacities are integers, you know, in a network, then there exists a max flow where all the there's exists an integer max flow, meaning that on every edge we would push integer number of flow units. Okay, so this setting where we saw that, you know, there's one coming in and this is split into half and half would not happen if all the capacities are integers. And this sort of follows by the Ford-Fulkerson algorithm that we saw in previous talks. Okay, so we're going to need this assumption. We're going to need the assumption that if we are given to the max flow problem a network where all the capacities are integers, then the flow that it gives us is a flow where all the, you know, all the individual flows on edges are also integers. They could be 0, they could be 1 in this case, but not more, but not 1/2, for example, right? So the claims that we want to say about this reduction, we want to say that, you know, really a max flow in this graph corresponds to a matching in the original graph. Okay, so that's the correspondence that we want to prove. Okay, so we want to argue that there is some kind of correspondence at any matching M in the original graph. So let's say on a bipartite graph, G correspond to some, let's call it integral flow. Integral flow means that all the, you know, the flow on each edge is an integer. Integral flow of the network G tilde, where G tilde is, you know, this network that we collected from the graph G. Okay, so we want to show that there's like a one-to-one correspondence here, and also that the size of the matching equal to the value of the flow. Okay, so this is the flow F. Okay, so let's see, there are two directions here. We want to show that for any matching in the original graph, there's a flow in this graph. Let's call this graph G tilde. And the original graph is just this, you know, this bipartite graph that look like that. Right, so this is G and this is G tilde. So let's say that you have a matching in G. How would you get a flow in G tilde? Well, you would want to push one unit of flow on every edge in the matching. And you also need to push, you know, some flow from S and some flow from T to T. So what you're going to do is you're going to sort of make this flow legal. So let's say that here you wanted to push one unit of flow. And here you wanted to push one unit of flow. So you also need to make it legal. So for everything in L that pushes one unit of flow, you're also going to insert one unit of flow. And everything else is going to be 0, let's say. And then everything in R, you're going, if something arrives to R, to a vertex in R, you're going to push it forward, right? So this is sort of like a proof by example, but let's see now how we can prove it more generally. Right. So the claim is as follows. Suppose M, so there will be two claims. So the first one is suppose M is a matching in G, then there exists an integral flow on G tilde whose value is exactly the size of M, right? So that's the first claim. And the second claim would be the other direction, that if we have an integral flow on G tilde, then we also have a matching with, this, where the sum of the matching equals to the value of the flow. So this is sort of like an if and only if correspondence between these two objects. So let's see the first part, this claim, right? So we sort of already said it in words. So how are we going to, construct the flow given the matching, right? So we're going to push one unit of flow on every edge in the matching. Right, so the edges in the matching, they also appear in the graph G tilde. So we just push one unit of flow on all the edges in the matching. So let's denote by L of M. This would be, the vertices in L touching M. And similarly, R of M would be the vertices in R touching the set of edges M. So we're going to push one unit of flow from S to V for any V in Lm, right? So every vertex on the left who touches the matching, we need to push one unit of flow from S to this vertex, so that this vertex would be able to push this unit of flow forward to the right-hand side. And similarly, we're going to push one unit of flow from V, or let's call it maybe U, from U to T for any vertex U in R of M. Okay, and this is exactly what we had in the previous proof by picture. And this is a legal flow, right? So, and everything else, we're going to push 0 units of flow. So this is a legal flow because as you can check, for every vertex, the incoming flow equals to the outgoing flow, okay? Except for S and T, which is the definition of a legal flow. What is the value of this flow, right? The value of this flow is how much units of flow we are pushing from S, and this is exactly the number of vertices in L of M, which is exactly the size of M, right? Because every edge in M touches exactly one vertex in L of M, and vice versa. Sorry, this is the value of the flow. Right? So we prove this one direction. Yeah, so I guess I want to see if there are any questions so far.
We haven't had many in the chat yet, but people are welcome to raise their hands right now.
Right. Okay.
Oh, how do we guarantee that the maximums are equal? But I'm guessing that's the next part of your...
Yeah, so what we saw so far is that if we have a matching on G, then we have a flow on G tilde. It could be that maybe the maximal flow on G tilde is even bigger than that, but we will see next that it's not the case.
Right. And someone wants to see your previous slide, I think. Is that what you're asking?
So you want to see the example? Okay, so in this example, right, so if this was like, let's see it again, this example. So let's say that this was the matching. So I'm just going to push one unit of flow on every edge in this matching, one unit of flow on every edge leading to the vertices, that we called L of M, right? So L of M are going to be these two vertices. And we're going to push from R of M, these two vertices, one unit of flow. And everything else would have 0 flow on it, right? And you can see that, if you look at the flow here, the flow is 2. Also here, the flow is 2, right? I mean, that's by definition of flow. So for every cut, the number of flow units that we move from left to right is exactly 2, which is a value, the size of the matching that we started with. Okay. In this case, for example, it's not the best one because we can also add this edge, right? So we can, in fact, increase these flows to be like that, and then we see that the max flow is actually free. Okay. All right, so let's go back. I want to show now the other direction. I want to show that if we have a flow on G tilde, then we actually also have a matching, right? This is maybe more interesting because it's less clear why it must be the case, right? So that's the second claim. If f is an integral, so that will be important, right? That all the flow units are integers. They couldn't be like 1/2. They could be, in our case, only 0 or 1 because the capacities were 1. Okay, so if we have some integral flow on G tilde, then there exists a matching M on G such that the value of the flow equals the size of the matching. So you can sort of look at the flow and take, come up with a matching if you look at the flow. So how are you going to do that? It's going to be very similar, but with maybe one important observation is that, since capacities in G tilde are all equal to 1, the flow on each edge could be either 0 or 1, right? It must be an integer. It's an integer that is at most 1, so it could be either 0 or 1. Right? So, and how are we going to get the matching? Well, we take the matching to be all the edges between some UV edge, where U is in the left-hand side, V is in the right-hand side, and the flow from U to V equals 1. Okay, so we're just going to look at all the edges going from L to R, such that the flow pushes some unit of flow on these edges, and we're going to pick all these edges. Okay, and now the question is, why is this a legal matching? Okay, so the first thing that to note is that the size of M equals the value of F, and this is just because why is that? Because if we look at this cut where we have S on one side and all the vertices in L on one side, and we have R on the other side and T also on the other side, then you can see that the value of the flow is exactly the number of it's exactly the number of edges that crosses its cut on which we push 1 unit of flow, right? We know that the value of the flow on every cut is equal. So in particular, it's equal to value of F. So this means that the size of M would be the value of F. Now, but we still haven't shown that M is a matching. Why is this the case? So this will be just by construction, right? So what do we know? We want to show, let's say, that every vertex here in L is connected to only one edge in M. Okay. What could be a possible bad case? It could be that we have some vertex here, U in L, sorry, that is maybe connected to 2 other vertices in R, and both of these edges were selected to the matching. So it could be that this is in the matching, and this edge is in the matching, right? So is this possible? Is this possible that we would pick these two edges to the matching? Or in other words, that the flow pushes one unit of flow on both these edges? Well, the answer is no, as you write in the comments. But why is that? So recall that U has only one edge coming into it, right? It only has one opportunity to get some flow in, right? The one from S. And we know that on every edge that he pushes like a positive flow, it must push one. So it couldn't be that he pushes one here and one here, because then it would violate the flow, right? The incoming flow is smaller than the outgoing flow. So this is impossible. So we showed that every vertex on the left-hand side only touches one edge in M, right? So there's no collision on the left-hand side. What about the right-hand side? Very similar argument, right? We can say that since we can push at most one unit of flow to T, we cannot get more than one unit of flow, right? So it couldn't be that we have like two of them with one unit of flow going into the same vertex V, because then, you know, V would have two units of flow, but it can only push one. So this would violate the flow equalities, right? The flow constraint. Okay, so I sort of drew you a picture. Of course, you know, I could have written it in words, but due to, you know, lack of time, let's not write all the proof formally, but just you know, look at this proof by picture. And what we got is that, you know, M is a matching because F is a flow, and every vertex in L can get at most one unit of flow in, and every vertex in R can push at most one flow out, right, to T. So because of these two things, we see that actually it's a matching. It could be, by the way, that some vertices are not getting any flow and not pushing any flow, right? So in particular, in this example that we saw earlier, right, the left side had 3 vertices and the right side had 4 vertices. So definitely it couldn't be that we can match up everything on the right-hand side, right? Because we have simply too many vertices there. We couldn't match up 4 hospitals to 3 doctors, right? This would be impossible. Okay, but we can push either 0. Sorry, we can match either 0 or 1 to each vertex. Okay, so now that we've seen this, and this is actually, I think, very, very interesting application of max flow. It sort of gives us a very surprising application that we can, right? We can solve these problems that seems nothing to do with the problem of max flow. We can solve it by a simple reduction, a reduction that sort of takes the graph, you know, is doing some pre-processing on it, introduces maybe 2 vertices and some edges, and we solve the max flow problem on this new graph. And from that solution, we can get a solution to the bipartite matching problem, right? So it's kind of surprising. And notice that we didn't need to even know how the algorithm for max flow works. I mean, the only thing that we need to know is that it has this fact that if all the capacities are integers, also the flow would be all integers, right? So that was the only thing that we relied on. I mean, if you come up with another algorithm that satisfies this thing, you can use it also to solve bipartite matching, right? So that's the beauty of reductions, is that we sort of relate 2 problems in a way that if you solve, you know, one of them, you can solve the other, but it's sort of in a black box fashion, meaning that if you improve the solution to one, you immediately improve the solution to the other. You don't need to sort of redo the algorithm or something like that, right? So that's very, very neat. And we will see also the connection between reduction and actually hardness, or intractability. We will show that some problems are likely very hard to solve because they are at least as hard as thousands of problems that nobody knows how to solve. And this is something that we will see probably in the next meeting, and this is what's called NP-complete problems. Okay, so I want to abstract away what we did here. Yeah, by the way, we can analyze the runtime. It's polynomial time because even if we do the SIPO for Fulkerson, it just increases the flow by at least one in each iteration. Because if you think about it, the network that we build had maximal flow, which is at most the number of vertices in it, right? So the number of iterations that we're going to need to do to push flow is at most n, the number of vertices. So this entire algorithm would run in time m times n. Okay. All right, so now I want to get to the main point of today's talk, which is the notion of reduction. So reduction in high level or sort of intuitive sense, would tell us that, a problem, let's call a problem A, reduces to a problem B if any subroutine to solve B can be used to solve A. If you are thinking of it as programming, think of it as follows. What is a reduction? It sort of tells us, let's say that you have some functions that can solve, the problem B, and then you want to solve problem A. So what you're going to do, you're going to do some kind of pre-processing, and then you're going to call the subroutine that solves problem B on some input, and then you're going to look at the answer and maybe do some post-processing, and then use that to get the solution for problem A. So you don't even need to look inside B. You don't need to look inside how what algorithm you use to solve problem B. You can just use it as some kind of black box and call this black box. Okay, so let's see it a little bit more in more detail or less abstractly. So let's say that we want to solve some problem A, right? So I'm going to build a box that solves the problem A from a box that solves problem for B, the problem B. Okay, so I have some box here. Okay, so inside I will have a box for B, let's say. Okay, so this box for B, can solve this problem, let's say max flow. Okay, and outside we want to solve some other problem, let's say bipartite matching. Okay, what are we getting? We're getting some input X. And what we're going to do is we want to take this input and do some kind of pre-processing on this input. Okay, so this would be a pre-processing step. Right, and after the pre-processing, we're going to get some, we're going to get some input Y. Okay, the input Y would be a natural input for the problem B. In particular, what did we have in this example? We took an undirected graph, a bipartite graph. We pre-processed it into a network with capacities that was directed, right? So we changed the problem a bit, right? So Y was some function of X, but it wasn't of the same type of X. And then we run the algorithm for max flow, right? So we run this subroutine B and we get some answer back. So let's call it B of Y. And now we want to do some post-processing, right? So we got the flow, but a flow is not a matching. So we need to go from a flow to a matching. So we need to do the post-processing, which extracts the answer to the original problem, A of X, from the answer B of Y. Okay. It could be, by the way, that the post-processing also, looks at the input X. So it could be that, we also have this line here. Sometimes it would make a little bit more sense to have this, but, anything that you can do with just the answer getting from, from this subroutine B and maybe from the input that you already started with. Okay, but let me erase this error because this is not how it's presented in the book, but you can always do it. Okay. So this was sort of like an abstraction of what a reduction is, and notice that once you have the reduction, if you have now an efficient algorithm for problem B, and the pre-processing and the post-processing were efficient, then automatically you get an efficient algorithm for A, right? What would be the algorithm for A? Do the pre-processing, apply B, and do the post-processing, right? So this shows us that, an efficient algorithm for B implies an efficient algorithm for A. And right, so here it's important to say that these things are, these pre-processing and post-processing are efficient procedures, right? So both of them are efficient. Notice that a reduction is defined only by this pre-processing and the post-processing. We are thinking of this box B as a black box. So a reduction does not include the solution for B. It just includes, how you manipulate the input X so that you would get an input for the problem B, and how do you manipulate the output B of Y so that you would get the output for your question, A of X. Okay, so a reduction is composed of these two mini algorithms, the pre-processing and the post-processing. Okay, so a reduction equal to pre-processing plus post-processing. And sometimes one of them would be very simple. So sometimes the post-processing would be doing nothing. Sometimes you would just get the answer from B, and this would be also the answer for A of X. But sometimes we will need to do more involved things, as you can see in the example that we already showed. Now, okay, so this line is sort of very clear, right? So, right, if we have some very efficient solution for B, then we have an efficient solution for A because we just do, pre-processing, B, post-processing. But notice that we can also turn this arrow in the other direction, right? So if something implies something else, then the negation of the something else implies the negation of the original thing, right? So if there's no efficient algorithm for A, then there's no so there's not exist an efficient algorithm for it, then there doesn't exist any efficient algorithm for the problem B. Okay, so when we are doing a reduction, we are actually, right, so if we believe that the problem A that we started with is a hard problem, okay, so for example, the traveling salesperson problem is considered a hard problem. So if we're able to show that, there's another problem B, so that if we solve B efficiently, we can also solve the traveling salesperson efficiently, then this is sort of can serve as indication that maybe this other problem B is hard. because maybe we don't believe that you can solve efficiently the traveling salesperson problem. And don't worry if you are not familiar with this. I will tell you in much details all these. If you don't know the definition of the traveling salesperson, I will tell you what it is, and we will get into more details in the next few lectures. But this is important to keep in mind. Right? A reduction can help in designing algorithms, but it can also help in proving hardness, right? Because this error goes in both directions. Okay. So I guess this was a slightly conceptual slide. So it will be good if you have questions. I would be happy to answer any questions.
We've been discussing integer versus non-integer flows and their reductions in the chat, and I think that we should circle back to it at the end of lecture if possible. Other than that, I think we don't have many questions.
Right.
People should raise their hands right now. Somebody's asking, is A supposed to be the max flow problem? But I think this is just a abstract example.
Right. So this is an abstraction of this example that we saw. So you can think of the beginning of today's lecture as an example of one reduction, but actually there are many examples that you already saw. So maybe it will be a good time to ask you, did you notice that you've seen reductions already in the class, or maybe in the exams, in the midterms? I will give you a hint that in the first midterms, we had, I think, 2 problems that were reductions, actually. Can you spot them? Right, so yeah, so very good. So both the problem on Dijkstra and the problem on inversion, one solution to them was a reduction. Okay, so for Dijkstra, if you remember, we asked to find, right, so we had this weighted graph, and we asked to find the minimal path between some S and T. And among the minimal paths, we asked the one that uses the fewest edges, right? And there were a couple of solutions to this, but one of them was to change the weights and to add like a very small epsilon, let's say, to all the weights. Okay, so maybe to add like 1 over the number of edges to all the weights. And then just run Dijkstra. Notice that this is a reduction. Like no matter how Dijkstra is implemented, if it gives you the shortest paths, then you would get a solution to your question. So in some sense, it sort of is taking Dijkstra, putting it in some black box. The only thing that you rely on is the fact that this black box is computing the shortest paths in this, new graph G tilde. And based on that, you get, this new shortest path with fewest number of edges in the original graph G. So this was one reduction. The other one was this question about inversion. In lecture, we showed how to look at one array and count the number of inversion in it. And in the exam, we asked, you get 2 lists of preferences, and you want to count the number of inversion between these 2 lists. And one solution was to sort of relabel everything and get back to this problem with one array, and then use the solution from lecture. So this is a reduction. You did some pre-processing, and then you used a solution that was already given. We actually, probably in the homework, you used a lot of reduction, right? So every time that you use, I guess, a known algorithm that solves some known problem, you are actually, if you think about it, if you're not opening up the algorithm, then you're using a reduction, right?
We have one more question.
Yeah.
So what does it mean for the pre-processing and the post-processing to be efficient?
So as algorithms, right? So we want them to run in time, which is, let's say, polynomial in their input. Sometimes it will be very efficient, so maybe linear time. Sometimes it will be, that each bit of y depends on like constant many bits of x, so it will be even super efficient. So the most general notion would be just polynomial time algorithms. Okay, so any algorithms that work in polynomial times, this would be very important once we get to NP. But if we care really about the running time, in a more precise way, then we actually want the reduction to be sometimes linear time. right? So in the case of bipartite matching and max flow, the reduction was really sort of linear time, right? So we did some kind of very simple manipulation on the input that would require only linear time. So this means that, you know, the running time of bipartite matching is more or less the running time of solving the middle part, right? Just the max flow part. Right. So in most cases, the reductions should be negligible compared to the time that it takes you to solve the problem B. Okay, so I guess in the remaining of today's talk, I want to show you a little bit, you know, more examples of reductions. I think some of them are very interesting and maybe right. So and I'm not sure that all of them are in the book, so it might be nice to know some of them. Okay. Yeah. So maybe let's. So the next example of a reduction that I want to do is on matrices, right? We saw earlier that there's a very interesting algorithm for matrix multiplication by Strassen. And this algorithm was running in like, I don't know, 7 to the log 2 of n, which is same as n to the log 2 of 7. Right, it was better than n cube, where the algorithm, the trivial algorithm works in time n cube, right? You call that you have like n by n matrix A, another n by n matrix B, and you want to compute some matrix C, which is a pointwise multiplication of A and B. Sorry, not the matrix multiplication of A and B. Right, and the natural, like the most naive algorithm is just to, you know, multiply every row in A with every column in B. This would take you n cube time, but we saw a divide and conquer algorithm that runs more efficiently. And, you know, there's a lot of literature about matrix multiplication, and there are a lot of very complicated algorithms. And, you know, the running time was shaved from n to the 2.8 to n to the 2.6 to n to the 2.5. And today the best known is like n to the 2.37 or something. And, you know, more complicated algorithms that we would like to you know, teach in this class, but very beautiful and rely on a lot of beautiful mathematics. And there's a belief that we can push it even further, that the best thing that can be done is almost n squared. Okay. And now I want to show you that actually matrix multiplication is very related to the problem of matrix inversion. Okay, so recall what is matrix inversion. So let's say we get some matrix A, which is n by n, and we want to compute A inverse. Okay, so sometimes it doesn't exist, but let's say that if it doesn't exist, and we say that it doesn't exist. So what is A inverse? It's a matrix, right? So what do we know about A inverse? We know that if we multiply A by A inverse, we get the identity matrix. Okay, so now you can ask yourself, you know what? These are two very different questions, you know, multiplication and finding the inverse of a matrix. We can find the inverse of a matrix using Gaussian elimination, which also takes n cube time. And, you know, maybe you can start thinking of divide and conquer, and maybe you see that the trick of Strassen actually work also for matrix inversion. But what I want to actually tell you is that these two problems are equivalent. So if you improve the running time in one of them, you improve the running time in the other, and vice versa. This is somewhat surprising. And this, like the second question on inversion, is also related to the question of how much time it takes to solve a system of linear equations, right? So more or less it tells you that if you improve matrix multiplication, you also improve the time it takes you to solve a system of linear equations. Okay, so I'm going to show you just a reduction in one direction. So I want to show you that if you can compute inverses, then you can also multiply. So I'm going to show a reduction from matrix multiplication to matrix inverse. And this is a, you know, a cute algebraic trick. So you get two matrices A and B, and you want to come up with some other metrics such that if you know the inverse of this matrix, you know the multiplication of A and B. So, I mean, to come up with it requires some ingenuity. I mean, I look it up online. I have no clue how they figured this out. But if you write the following block matrix, so you have, so this is an n by n matrix. This is an n by n matrix. And here you have, 9 block matrices. Each one is n by n. So overall, this is a 3n by 3n matrix. Okay. So what do you put on the blocks? So on the diagonal, you put the identity matrices. On some of these entries, you put the 0 matrix. And on this block, you put A, and on this block, you put B. Okay. And now you assume that you have a very fast algorithm that can invert matrices. You ask this matrix, this subroutine, what is the inverse of this matrix? Okay. And you can verify that the inverse of this matrix equals this thing, okay, as block matrices. Okay, so on the first block would be identity, the second one would be minus A, the third one would be AB, and so on and so forth. So you see that one of these blocks would be the multiplication of these two blocks A and B. Now, how can you extract the matrix multiplication? Just, what would be the pre-processing? You just take A and B and put them in this bigger matrix, which is 3n by 3n. What would be the post-processing? You look at the answer, and you just take this top right block. This would be the answer. Okay, so if you can solve inverse faster, then you can solve matrix multiplication faster. And there's actually a reduction also in the other direction. And since this reduction is not really increasing the input length by much, it's only increasing it by a constant factor, then actually running time T of n for one implies running time O of T of n for the other, and vice versa. And right, so this means that these two problems are, have the same asymptotic behavior, like in terms of the best algorithm for one is would run in the same time as the best algorithm for another. So that's kind of neat. And actually, there's a lot of algebraic problems, like taking a polynomial and evaluating it on many points, interpolating a polynomial from these values. So there's like an entire book. And in all of these problems, you're sort of reducing this question about polynomials or matrices to one of two questions. One of them is matrix multiplication, and the other is polynomial multiplication, or FFT. So you already saw like these two building blocks, that from these two building blocks, you can more or less create like dozens of algorithms. So I just thought that it was interesting. Okay, so this was sort of in the realm of things that we can compute efficiently. Right? It sort of tells you, if you get something that works better for inversion, better than Gaussian elimination, then you get something better for matrix multiplication. Okay, and there's also another direction that I haven't showed you that is a little bit more complicated. Okay, but I want to show you one example, which is maybe more important going forward. And this is about problems for which we don't know an efficient algorithm. Okay, so I want to now reduce two problems for which we actually don't have any efficient solution to any of them. Okay, so this would sort of relate the hardness of one to the other. Okay, so this problem, it was first mentioned in the 9th century, so more than 1,000 years ago, by a person named Rudrata. Okay, and he was interested. I guess he was interested in chess. So he was asking, is there a sequence of moves that a knight could take on a chessboard, such that the knight would visit each square exactly once, and also come back to where it started? Okay, so let's say that we have this, let's see. Right, so you have a chessboard 8x8 and you start here, and every time you make a move, you make a knight move. So maybe you move here, and then maybe here, and here, and then here. Okay, so you make a sequence of moves, and then you want to tell whether you can visit every square exactly once, and then come back to where you started. Yeah, I forgot where I started, but let's say maybe it was here. Right, so that's an interesting question. I remember that my friend in high school tried to program it, and it took quite a lot of time, maybe for a good reason. And more generally, you can think of this problem in general graphs, right? So like this problem on chess is very nice, and actually there are probably much known about this problem since this was studied for more than 1,000 years. But more generally, we can talk about general graphs, right? Let's say undirected graph. And we can ask, to find a cycle that visits all vertices once, exactly once, right? So that's a question, right? So some graphs would not have this cycle, and the question is, maybe to tell whether a graph has this cycle or not, and also to find this cycle. Okay, so what's the connection between the problem on this chess and the graph, right? We can just, how do we abstract it? We can just have vertices for each square, right? And we connect two vertices if there's a knight move that goes from one to the other, right? So we have some connections like that. And then this question, like if we know how to solve this question on general graphs, then definitely we know how to solve it on this chess problem, right? It turns out that this question about Rudrada cycles is what's known as an NP-complete problem. We'll get to what does it mean, next week. But it's actually a hard problem. We don't know of an algorithm that works on general graphs and that works efficiently in the worst case. And we will show that there are good reasons why we don't know that. Okay, so let's say that we believe that this problem is hard, this Rudrada cycle. Right. So now I want to ask about another question, which is, a variant of this question, Rudrada path. So you get a graph G, undirected as before, and you get also a source S and target T. And your goal is to find a path from S to T that visits all vertices exactly once. Okay, so that's a slightly different version of this question. I mean, it's not the same question because in one we are asking for a cycle, in the other we are asking for a path, and also we specify the starting point and the end point. So maybe you are giving me this specific location in the chessboard, and you're asking, can I start a path from here? And maybe I want to end, I don't know, here. So maybe here this is S and this is T. Okay, so this is a slightly different question, right? So what I want to show is that actually, if you can solve one, you can solve the other. Okay, so let's say that you knew how to solve the Rudrata cycle problem. Okay, so you had some that could solve the Rudrata cycle problem. And now I'm giving some graph G with source T and source S and target T. And I want to solve the Rudrata path problem. How I'm gonna, pre-process this input, which gives me a graph, a source, and the target, into a problem that just ask for a cycle. So what would be the idea? The idea is to take this The idea is to take this graph G, right, that has these vertices S and T, and to add one dummy variable, dummy vertex. Let's call it X. Okay, so this will be a new vertex that didn't appear in G, and we're going to connect X to both S and T. Okay, so this is an undirected graph, so these edges don't have any direction. And now this would be like my new graph. Let's call it G prime. Okay. So the idea is that, I'm going to get G, S, and T. This will be the input. Then the pre-processing would spit out G prime. Okay. Then I'm going to feed G prime to the Rudrata cycle, black box. This would tell me either, that there's no cycle, or it would tell me, yes, there is a cycle and this is a cycle, right? So maybe like a list of vertices according to the order of the cycle. Okay, so now what we're going to do, if there's no cycle in this graph G prime, we're going to say that there's no Rudrata path in the graph G. So then we would answer no. And if there is a cycle, we would answer yes. And then the question is, what would be the path, right? So let's look at it. So let's assume that there's a Rudrata cycle in this graph G prime, right? So it's a cycle that visits every vertex once. In particular, it must visit X once, right? So the cycle would be maybe, X going to S, going to something else, going to something else. Eventually, we would reach to T, and then we have to go back to X, right? So every cycle would have this structure. Why is that? Because X is only connected to S and to T. So there's only like two edges touching X. And in a cycle, every vertex must touch two edges. So we must use these edges. Okay, so we start with X. We can go either to S or to T. So let's break ties and go to S. Then we go along the cycle, and eventually we need to come back to X. So we need to come back, and we need to come back from a different vertex, right? Because we are not allowed to visit the same vertex. So every Rudrata cycle in this graph G prime must have this following form. And therefore, if we just remove this first edge and the last edge, what do we get? We get a path that is in G, starts in S, ends in T, and visits every vertex in G exactly once. Okay? So here what we're going to do is we're going to remove the edges XS and TX from the path, from the cycle, and this gives us a path. Okay. So let's do it maybe a little bit more slowly. Right? So the claim is as follows. If G is a Rudrata path from S to T, then G prime as a Rudrata cycle. Is this part clear, right? So if we have some path that travels through all the vertices in G exactly once and starts at S and ends in T, then definitely when we add this X and add these two edges, then we can make it into a cycle, right? We just add this edge and this edge. And we want to say also the other direction. If G prime is a Rudrata cycle, then also G is a Rudrata path. From S to T. And how do we get this path? Well, we just said it like 2 minutes ago. We just take this cycle. X should appear at some point. So let's write it as the first vertex and the last vertex. And then we notice that we must visit S after visiting X, and we must visit T before visiting X. So the cycle must be of this form, so we can remove the two, the first and the last edge, and we get a path. So we see that like there's an if and only if. There's a Rudrata path between S to T in the original graph, if and only if there's a Rudrata cycle in this graph G prime. Okay, and moreover, we can sort of, manipulate the answer to one to get the answer to the other. Okay, so morally, what does it tell us? If we believe that solving Rudrata paths is hard, what do we get by that? We get that also solving Rudrata cycles is hard. Why is that? Well, if we have an efficient algorithm for cycles, we also have an efficient algorithm for paths, right? Because we can just take pre-processing, efficient algorithm for cycle, and post-processing. So this shows us that this problem of, right? So let's write it in. Right, so we have this reduction from Rudrata path to Rudrata cycle. Now, if we also have an algorithm for Rudrata cycle, that's great, because then we'll get an algorithm for path. But unfortunately, we don't know an algorithm for each one of them. So what does it tell? It tells that this problem is at least as hard as this problem. Yeah. Yeah. Right. So if we believe that this problem is hard, then this implies that the cycle problem is hard as well. Okay, so this would be a great time to ask for questions. And by the way, we would get back to these hardness reductions in the next lecture, but I want to show you both reductions in the sense that they give us efficient algorithm, and reduction in the sense that they sort of connects two problems we believe both of them are hard.
Feel free to raise hands. I don't have something immediately to bring up. Let me check if anyone's raising their hand.
Right, so there's a question about, what about the other direction? Is this, can we have a reduction from cycle to path? It's a very good question. Yes, we can. I mean, thinking of this reduction on the spot is a little bit hard. So sometimes it will take some time to come up with these creative ideas to manipulate one to the other. But actually what we'll show is that there's like a large collection of problems where Rudrata path and Rudrata cycle are among this family. And there's a reduction between any two of these problems. These are the NP-complete problems. So these two problems are equivalent to one another. Yeah, it might be probably like a good exercise to think how to reduce it in the other direction.
If we have time, there were some questions from earlier in the lecture about integer programming and linear programming, and whether or not we could translate a instance spit out by simplex with subflows that have non-integer flow values, and then with scaling, the numbers translated back in as a post-processing effort.
Yeah, so that's a lot harder. So okay, so if the flow that we get, let's say that we have some other algorithm that does not guarantee integrality, right? So that's not the guarantees that if we give it integer capacities, then the flow would be composed only of integers. Then it's not that clear how to get back the answer, right? And this is actually a problem that is sort of very inherent in a lot of in coping with NP completeness. So a lot of problems can be described as some integer versions of linear program. And if you reduce the integer constraint, the fact that you want variables to be either 0 or 1, then you get just a simple linear program. And we already know that simplex solves linear programs. But then the question is, then you get an answer back from simplex, but it gives non-integer values to the variables, and you want only integer values. So how do you get it back? So there's like, people spend years thinking of this problem. So in different contexts. So sometimes you can think of the values, maybe you should round them up. Maybe you should do some kind of randomized rounding, where you think of, if the value is closer to 1, then with high probability you would sample 1, with low probability you would sample 0. So and it's really very complicated to analyze how these things work. In some cases it has a nice solution, but in general there's no proof from the book of how to get from a fractional solution to an integer solution, and for good reasons. So to get the integer solution is also an NP-complete problem, and the linear program is a problem that we know how to solve efficiently. So the difference between the two is really stark. There's a big difference between these two problems. Yeah, so just to mention, right, so to bring it back to the context of today's lecture. So today we talked about, this black box problem of max flows, but we needed to assume one thing about it, and that the thing that we need to assume is that if it gets integer capacities, then it outputs an integral flow. That's the only thing that we needed for the proof to work, and based on this property, we were able to solve the bipartite matching problem. Okay, so yeah, in some sense, this was a little bit different, let's say, than the other reduction. In the other reduction, we didn't need to assume this, caveat that solution has this very nice property. For example, here, no matter how you come up with an algorithm for Udrata cycle, this would give you an algorithm for Udrata path. Okay.
All right.
All right.
If I've missed any questions, everyone should feel free to raise their hands.
Someone's asking if we can review the slide of Udrata path.
Thank you.
Mm-hmm. So so in this slide we only defined the two problems, and in the next slide we showed the reduction from one to the other. Yeah. Maybe if we have a few minutes, does anyone want to try to do a reduction in the other direction? I mean, I don't remember it off the top of my head, so if anyone can come up with a reduction, that would be nice.
I am thinking to create a dummy duplicate vertex of the source.
Mm-hmm.
So if S is like the start of the cycle, just make another S prime, and it has all the edges to the edge S has, and then I think the runtime will just be OE, I guess. So
you want to add just a dummy source or also a dummy target?
I just want to add a dummy target, which is a replicate of the source.
I see. Okay. Yeah. So maybe what you're saying is like, so let's say that we have a graph G, and maybe we add like a source S, and we connect it to all other vertices, and also we make S equals to T. And now actually, yeah, we can just, right. So one thing that we can do is, without even that, we can just identify some. We just take S to be equal to T, right? And then we ask, is there a path from S to T that visits every other vertex at most once? This path would be actually a cycle. So I guess this is a way to reduce the other to one to the first, right? So here we are actually not doing anything. So we get G, and the pre-processing would output just G, S, and S for some vertex S. And then we ask, find a Rudrata path from S to S. If we did it, then we've actually found a cycle in G, right? So that's, I guess, a reduction in the other direction. And it might be a little bit more annoying if, right, if we require also that S is different than T. So let's not require that. So that the reduction would be nice.
Yeah, so maybe when in the pre-processing, we can somehow allow S can be visited twice, and then I think you'll be naturally solved.
Yeah. Okay. So anyway, it's a cute exercise to think about, so maybe if you come up with a solution next time where the source and the target are not the same, it would be nice to discuss it. But I think that maybe it's a good idea to finish a little bit early today, and next time we would meet the very famous question of P versus NP, and we will talk more about reductions and NP complete problems. Okay.
All right, I'll stop the recording.